Hello, good evening. Hope you can hear me and see my screen clearly. If not, please let me know. Welcome to the week 9 live session of the CS104 course. Okay, great. Good that you can hear and see. So let's get started. So I will skip over the logistics. I think all of you are familiar with it. So before we jump into the recap of week 9, hopefully the course is going well for all of you. I think 9 out of 12 weeks are complete. So we will have 3 more live sessions. So this is a good point to again ask what I usually ask, right? Are you having any issues with some week's content? For instance, if you've started revising and you feel that you still don't have a good hold on a particular week's content, you would like some additional explanation, things like that are also fine, right? Because we don't have extra live sessions for revision. So if you're having difficulty with some topics from any of the weeks covered so far, you can always let me know in chat, and then we'll try our best to cover that in the next sessions. So, good evening. Yeah, I'm okay. Let's continue. So, week 9 was two parts. The first part was a continuation of the deployment, and the second part was accelerating different parts of the data science pipeline, right? So, let's start first with the deployment part, which is using TensorRT. So, we already looked at what TensorRT is and how to use it, but here is again a quick overview that will help you understand. So, you have so UFF is a stands for Universal Framework Format, which is TensorRT's internal format to represent the network graph, and you can kind of use, so you can get to TensorRT using various frameworks, right? For instance, you could be writing a PyTorch model, you could be writing a TensorFlow model. So depending on what framework you're working with, you could kind of get it into TensorRT through different ways, right? For instance, you could use a model importer that kind of takes one of these framework models and then converts it. And you could also use like a common format. I think ONNX was something that was discussed. You could also do that and then get your model to TensorRT. Then the optimizer performs various optimizations as we studied in the previous weeks, right? Where optimizations that involve things like the batch size, the precision, the memory it takes, right? All, and we looked at particular optimizations like fusion and a bunch of other things, right? So TensorRT does a lot of those things under the hood, and ultimately it gives you an inference engine which you can kind of serialize and put it to a file, and you can have various files, right? Like this plan 1, plan 2, plan 3 that is shown. So this not only includes the weights but also a kind of schedule for the kernels to execute the network. And then finally, when you want to run it, so this is a way for you to store this optimized network, right? And one second. Yeah. Finally, when you want to run it, you fetch it from disk, you deserialize it from a file to a TensorRT engine object again, and then you deploy it. So again, we looked at various deployment possibilities last week. So we spoke about an embedded deployment, we spoke about a data center or a cloud deployment, and we also spoke about a hybrid deployment where you could kind of use some activity on the edge and some activity on the cloud. All of these are valid possibilities. So yeah, so this is the ONNX part, right? So here, this is an example. So we're talking about an image segmentation model here. So you convert it into ONNX, which is kind of a standard format. Now remember that TensorRT is from NVIDIA, but they have to deal with, if they support individual frameworks, they have to kind of support a lot of things, right? So one common thing that you will see various vendors and tool makers do is to support a non-specific format, a format that is common and sort of like a standard. So ONNX was proposed like that, where you can kind of convert between frameworks and different model types, and that's one of the reasons why TensorRT kind of heavily supports ONNX rather than individually supporting each framework, right? So that way, this is kind of a middle ground. If you have a model written in some other framework, you can convert it into ONNX, which is sort of neutral and something supported by TensorRT, and TensorRT will just take the ONNX model. So that's a good way for them to deal with this situation of multiple input frameworks. And then so once you have an ONNX model, TensorRT applies various optimizations and generates an engine, and then you finally perform inference on the GPU. So this is the TensorRT flow again. So if you look at the components involved in this, there is an ONNX parser which takes which kind of converts something which takes an ONNX model and populates a TensorRT network object. And then there is the builder component of TensorRT, which takes this network object in TensorRT. So this is basically what forms the pipeline, right? So this is the way you kind of look at it, at least till the engine. Let's look at the logger later. So builder takes a network and then generates an engine that is optimized for the target platform. Again, remember we spoke about these optimizations and spoke about how some of them are hardware specific, right? Because PyTorch and TensorFlow and most other frameworks are hardware agnostic. They don't perform optimizations specific to a particular hardware or a GPU. But TensorRT, since it's from NVIDIA, a hardware vendor, knows a lot more details about the GPU or the hardware that this is going to be executed on. And as a result, it performs a lot of optimizations that are very specific to that platform. And then finally, an engine is generated, as we spoke about in the previous slide. So this engine, so there are two parts to the engine, right, as we saw here. One is generating the engine, and you can serialize it and store it to a file. But when we talk about running an engine, it basically takes some input, performs some inferences, and gives you the output of the inference. And then logger is something that you use with the builder and the engine to capture errors, warnings, or what any other information you need either during the build phase or during the inference phase. For example, a very good thing that you may want to know, for instance, you've read that TensorRT does a lot of layer fusion or operator fusion, right? So you might want some information that tells you, that helps you quantify this fusion, right? How many nodes were there before? How many nodes are there now? So that was also covered in one of the lectures, and we will go through that in the recap. But if you wanted to know something like that, then the logger is a great way. So you can enable those logs and you will get information on how many nodes were there before, how many nodes were there after, and so on. So that is information, right? You can also capture errors, warnings, and anything else that you need. So that's the logger part of it. Yeah, coming to performance metrics, MLPerf inference is a industry standard inference benchmark, as this says. MLPerf also has training benchmarks, so you can go take a look at it. I don't know if it was linked in your slides, but I will share this. So for people who are not ML Commons, let me share an inference, maybe inference edge benchmark. So inference, so benchmarks are kind of a standard way to that helps you compare different hardware platforms and results on those hardware platforms. So for instance, let's say you have a 3060 GPU, right? And now someone tells you that, oh, there is this new 4090 GPU, and they say, oh, this is much faster and much better. So then you have this question, on what is it faster? What workloads is it faster? Then maybe someone tells you, I ran XYZ model on this GPU and its inference was very fast. So you run the same model on your 3060 and you say, okay, I got so and so results. And then as you start comparing, you find that, oh, this person has used a different parameter, maybe batch size. You used a different batch size. And so many other things like that, right? You might have used a different version of PyTorch, and all of these things play a role. So benchmarks kind of give you a standard way to compare hardware by standardizing all variables possible. Other than the hardware itself, most things are kept constant, right? For instance, the code itself. So benchmark code will generally be available from the benchmark library, and you can simply take that and run it, and then on your particular hardware, and that will give you some results, right? So you might have heard of so even for GPUs, right, vendors usually use some standard benchmarks that they compare performance against, because otherwise how do vendors know that they're making a better GPU? they probably conceptually have discussed it and have added more SMs or whatever, right? But till you have some standards across which you can qualitatively and quantitatively measure performance, there is no possible way to say something is better or something is faster, right? So benchmarks, so if you go look at this link that I've shared, you will see, for instance, very clear details on what scenarios are used, what is the duration for that scenario. You will see what metrics are used. So it's not simply enough to tell you that run inference on this particular model. I should also tell you what to measure. So then do I talk about latency, inference latency? And even if I talk about latency, there are so many various ways you can report it, right? I can tell you average latency, I can tell you median latency, I can tell you 99 percentile latency, right? So all these give rise to ambiguity and give rise to confusions about performance and how to measure performance. So benchmarks tell you the workload to run, the setting in which to run them, and also the metrics that you would report. So it becomes very easy to kind of compare performance, right? So MLPerf is one of those industry standard benchmarks. So every now and then they kind of update their workloads, and you can see on this page that there are workloads from classification, object detection, medical image segmentation, speech, language, LLMs, right? So across a wide variety of domains, vision, speech, language, and across a wide variety of models and data sets. And this a lot of hardware. So if you go look at the results, right, which I think is in the same. So if you go to the menu and you kind of look at the benchmarks, so you will see when you first open this link itself, on top you will see results, right, where you will see various vendors submitting, vendors and certain other people who benchmark these platforms. For instance, from NVIDIA you will see a bunch of edge platforms from the link that I shared, and you will also see some startups which are making some custom ASICs and things like that. So all hardware vendors run these benchmarks and submit their results to this. So that's a way for them to also authoritatively tell the public that, oh, this new hardware that I've made beats all other hardware on this benchmark, right? So everybody knows what is the reference, what is the baseline they're comparing against. So TensorRT is one of those. It shows better performance across all tests in MLPerf inference, and it accelerates models across data center and edge in various domains, right? Vision, speech to text, natural language understanding, and recommender systems. Okay, any questions or doubts so far? Or anything you'd like me to explain more in detail? We can do that in the next week. I think this week there were a lot of videos. There were around 6 or 7 lecture videos. So I think there's a good amount of recap. We might not get time to go into a lot of other things, but we can definitely take it up next week. So if you have any questions or comments, please let me know. Repeat again about benchmark. So this page will give you a good idea. You can, since we have been studying deep learning and machine learning, this is a very good benchmark for you to be aware of, right? So go through this after the session and you will understand what are some of the models that are used and what are some of the metrics that they ask you to measure. So that will give you an idea of what an ML benchmark looks like. But I was talking in the broader context also, right? You have CPU benchmarks, GPU benchmarks, you have memory benchmarks, IO benchmarks. So these are a standard way to compare the performance of workloads across hardware, right? Hope that helps. Any other questions? Why is it faster? Why is I'm not sure what you're talking about, but if you're referring to hardware, right? So basically, vendors try to make better hardware. And how do you measure the performance of that hardware? By running some workloads on it. And typically, or these in context of ML these are typically inference or training benchmarks, right? So it's faster because the hardware is better. Now, what do I mean by the hardware is better? Maybe the compute has improved. If you're talking about a GPU, compute from generation to generation definitely improves. The memory bandwidth also could have improved. For instance, if you see systems a good while ago, you would see that they are using DDR4. If you see recent ones, they might be using DDR5. So the memory bandwidth might have improved. My audio is breaking. Is that for everyone? If so, I'll try switching to a different mic. Can someone else confirm if my audio is okay? Anyone else? Or does everyone have issues? Okay, since no one else seems to be replying, let's give it a couple more minutes. And if any of you have issues with my audio or network, you have a lag or something like that, please let me know on chat. It's breaking again. Okay. I don't know if that's my network or your network. I did a sound check before joining, so I'll wait for someone else to confirm before I try and switch microphones. If anyone else has an issue, please let me know. Because if there's an issue, it'll likely be there in the recording as well. Breaking for some time and coming back to normal. Sounds like a network issue. Let me switch networks quickly. Okay, is it any better now? Or is it still the same? I have switched networks because I think my mic is fine. It's okay. Great. Thanks for bringing that up. Okay, so we were talking about benchmarks. Hope that part is clear now. Okay, let's move on to the TensorFlow TensorRT part, right? So this is also called TFTRT. So this is an integration of TensorRT into TensorFlow, right? Again, why do we do this? TensorFlow is a very popular framework. So apart from having the typical ONNX path, TensorRT also supports a direct integration. So you might see that with the most popular things, right? For instance, TensorFlow and PyTorch, you might see some additional support being offered. So here what happens is TensorRT optimizes and executes compatible subgraphs, and the remaining graph, the parts that are not really runnable with TensorRT, are still you going to use TensorFlow itself. So why would this happen? Remember that there was this discussion in the last week also, where we spoke about certain operators being supported with TensorRT and lots of other layers and operators not being supported, right? So this means that even if you try to use TensorRT throughout, some things might not be able to use it. And that's why this sort of integration allows a hybrid model. Whatever can be optimized with TensorRT is optimized, and the rest of it is executed on TensorFlow itself. So what happens here, TensorRT parses the model and applies optimizations to the portions of the graph wherever possible. And again, here is a performance result, speeds up TensorFlow inference by 8x for low latency runs of the ResNet 50 benchmark. So again, notice that it's reported on a benchmark. If I didn't have this benchmark part, this I'm assuming is the MLPerf benchmark itself. I would have to say ResNet 50 and then specify all the parameters that I've used. For instance, the batch size I might have used with it, and what other optimizations I might have done, what precision I'm running it, all of these things, right? So it would become a very long sentence and specification. So a very easy way to do it is say that I ran the benchmark and I got a speed up of so and so. So that's the advantage of the integration. And notice that revise the second point, okay? Parse the model and apply optimizations to portions of the graph. I think we have an example for this. So yeah, I think I've kept the example. So let's talk about that there. But broadly, a few optimizations that you can think of, for instance, is this layer fusion, right? So for instance, in this graph, you see that the initial model graph has a lot of nodes. It has around 46 nodes. And then you have a freezing of the model, which we'll talk about in a little bit. And finally, this is the TensorRT graph, right? And the TensorRT graph has only 13 nodes. So that is the TensorRT optimization side of things. So this part is basically about parsing the model and applying optimizations wherever possible. So in the example that we saw, an optimization was fusion. So from 40 whatever nodes, we went to 13 nodes, right? And TensorRT did that because those optimizations were possible to those portions of the graph. And before it does that, it needs to kind of parse the model and understand what are the layers in the model, where are optimizations possible. Yeah, so this is about TensorRT integration. So let's look at the workflow of this. So this part is in TensorFlow, right? So you can either create and train an ML model from scratch, or you could get a pre-trained model from some library, right? So I think we saw the PyTorch ones, we saw NVIDIA's Tau library. Give me a minute. Yeah, so you can get a pre-trained model also. What is the difference between the first and the second point? So the first point is an overall overview, right? It tells you what TensorFlow TRT basically does. Now the second point is kind of breaking that up, and it's telling you that what is the internals of it, right? It's like looking at this flow diagram. So if I were to overall describe this, I would say that there are some optimizations done, and then that helps you get a speed up. If I had to tell you in terms of steps, I would say, okay, you take a saved model and then you do some optimizations using TensorRT, and then you finally deploy it. That's all. There's nothing majorly different between the first point and the second point. Yeah, so you take a model through either of these ways, right? You take something that's already pre-trained and existing, or you create something from scratch and train it, either of those. Then you get a TensorFlow model. Now you optimize that using TF-TRT, and you get a TRT optimized model, and then that is ready to deploy. So you can either deploy it with TensorFlow itself or Triton Inference Server. That's the whole workflow. So I think you had an example which I've kind of put into slides as well. So let's look at that. So the saved model is also called a frozen graph. So once you have a trained TensorFlow model, you need to kind of create a saved model or a frozen graph of it, and then give that to the Python API of TensorFlow TRT, which returns the TensorRT optimized saved model. So think of the saved model as some format, right, that TensorFlow uses. So originally you will need to create this for your TensorFlow model, then give that to TensorFlow TRT, which will optimize it, but still return it in that same format, the frozen graph or the saved model format. And what would have happened there? Each supported subgraph basically whatever can be optimized and run using TensorRT will be replaced with a TensorRT optimized node, which is also called a TRT engine op. And this thing will basically be like a new TensorFlow graph. Basically everything that can run using TensorRT will be replaced by a TensorRT optimized node, and the rest will be run using TensorFlow itself. But this is saved in, it is saved in the same format, the frozen graph format. So let's look at code for that, right? So again, you have an import to use TRT, and you call upon the converter where you give the argument as your saved model directory. Then you ask your converter, TRT just stands for TensorRT, that's the official abbreviation, and you ask the converter to convert this, and then finally you save it. So the format remains the same. And the frozen graph is, again you have an import statement, and then you call the graph converter, and here instead of a model directory you use a frozen graph, and you give it some additional information. I haven't used this API, so I'm not really sure about what the blacklist refers to, but you can go look at the API documentation in case you want to know about that. And again you call upon the converter.convert. So again, in this conversion, you can pass a number of parameters. So for instance, you can tell it about the precision. You can talk about whether you want to use FP32, FP16 or int8. Then you can give a number of other parameters, for instance, the maximum batch size. And there are other flags sometimes, right? So you can only use this when a certain other flag has a certain value. This is one of those examples. So if dynamic op is false, then the max batch size is used. So this is the maximum batch size for TensorRT engines. And at runtime you can use a smaller batch size, but a larger batch size will result in an error. So again, some of these things affect optimizations, which is why you can't change them. You need to specify an upper bound beforehand itself. This is one of those examples. Similarly, you have a use calibration thing which is needed if it's int8. You have a minimum segment size, and is dynamic op. So the segment size, for instance, looks at the number of TensorFlow nodes that are needed for a TensorRT subgraph to be valid. So these are ways in which you as a user can kind of direct this conversion, right? So you can say the maximum batch size I'm going to use is this, or use int8, or things like that, right? So they will be reflected in the converted one. So here is the code. Let's look at that also briefly. So first you import all the libraries that you need, for instance the TRT and the conversion and all that, and then you save your graph, and then you restore the graph, and you convert it to a frozen model, right? So again we saw an example of this API. It's very similar here, and then you write it, and this will be used later for inference. That's basically it. Then so this is basically the convert to the frozen graph part, and this is the optimize to TensorRT graph. Again, this shows you all some of these parameters that we spoke about, for instance the maximum batch size, the precision mode, and taking an input as the frozen graph. Again, this TRT I myself haven't tried out, so a lot of these APIs are new to me, but you can try this out and let me know if you have any questions. Frozen graph means pre-saved model. Yes, kind of. That's the idea. And yeah, this is the final part, is saving the TensorRT model itself. So this was the demo that we were earlier looking at. So how many nodes are there before and after the optimization, right? So you can add print statements or even logs to see this. So before you pass it to TensorRT, you print the number of nodes in this frozen graph. Then you convert it to TensorRT and then print the TensorRT nodes, right? TRT engine nodes. Basically, these are kind of declared eligible to be optimized using TensorRT. They will be run using TensorRT. And finally, you also print the number of nodes, all the nodes that are there in the TensorRT graph, which is 13. So this is the initial model and this is the frozen model, and finally what you get as the TensorRT output looks like this. So you can visibly see that this looks very small, right? And notice that these are the two TRT engine ops. This is what is shown here. These are the TRT engine nodes, meaning that these are converted to TensorRT engines now. But there are various other nodes in this graph as well, and that's where the 13 comes from. So this is all nodes in the graph, but only some of them will be basically run using TensorRT, because those are the ones compatible with TensorRT. Those are the two that you see here. Yeah, with this we come to the end of the first part, the deployment part. So any questions or doubts or things that are not clear, I'll give you 1 minute, think about it and let me know, and then we'll move on to the rapids part of it. What is a TRT engine? So let's see if there was a definition somewhere here. I think it was there in the very first slide. Let me also see if I can find some documentation that will help you understand what it is. So broadly, you can think of this TensorRT engine as a runtime a runtime format for inference, right? Basically, if you look at a model storing format, for instance, if you look at the way models are stored in TensorFlow or PyTorch, you will see like an architecture, you will see weights, but TensorRT also includes information about the low level kernels that would actually be executed, right? So I'm trying to see if there's a way you can visualize it or understand it better, or the official documentation may be a good place to look at. Let me look at that and see. I can't find anything that would really help you visualize it better, but let's see, maybe I'll talk about it in the next class when I have a slide that I can reference it, and then um, yeah, I think this is a good definition. It's not from the NVIDIA official documentation, but this will probably help you understand. So it has, in addition to the model architecture or the weights, right, it has information about kind of running the model itself, right? So you can think of it as something very close to a runtime plan or a schedule. And you can also go through this blog post that talks about it in a lot of detail if you're interested. And we can see if next week we can have a slide or two on Tensorati engines and what they mean. Any other questions in the whole deployment part? Frozen model. Okay, let's again get some more details on the format itself. That will maybe help you understand. For now, just think of it as a format where you can save the model, right? And it's sort of frozen in the sense that it contains a lot of things that are saved as constants, right? For instance, they may be hyperparameters that you define, and um, they cannot be changed later on. So you're essentially freezing this whole graph, right? That's a easy way to understand it. But again, that's also something that we can touch upon in the next class. You understand the left part, okay? The right part is basically after the optimization, right? So we spoke about fusion in the last class, where we get a lot of benefits by merging multiple nodes into one, right? In terms of compute, in terms of the bandwidth. So that is something Tensorati does. But again, because of the number and variety of operations that are supported by Tensorati, not everything can be combined. For instance, I can't take this whole thing and then just convert it to one Tensorati engine. That would be possible if everything was Tensorati compatible, but typically it is not. So you might have some portion here that is sort of compatible that I can convert to one single Tensorati node, but there might be some things here that are not compatible. So I will have to retain them as TensorFlow layers themselves. And then again, I might be able to convert all of this into one TensorFlow node, one TensorRT node, and then there might be again some things that are not compatible. So if you look carefully at this, right, you will be able to see where these points are, and maybe you can take an example and try this out and do this visualization, right? So I think the visualizer used was Netron. So once you get a file in that format, you can kind of visualize it using this. So it will give you the same visualization that is here. and then you can see where exactly these conversions have happened. And for instance, you can clearly see that the softmax layer is kind of common and the input is there, and then after that a number of layers have been combined into this TRT engine, and then you see a shape and a data format operation, and then you see a strided slice, right? So you can, if you look carefully, you will see that that is somewhere here maybe, and that means that everything from here till that point has been fused into one TensorRT engine. And like we discussed before, this engine basically contains information about what kernels need to be run and how they would be run and things like that, basically the execution plan. And similarly, you can see what layers are not compatible. For instance, the strided slice is retained as is, the pack is retained as is, the reshape is retained as is, and after that whatever is there till you get to this before softmax, all of it is again mapped to one TensorRT engine output. So that's how you kind of understand these two. So these two happen as a result of this step. This step, right? You take a network and then you generate an engine. This step actually parse the model and apply optimizations wherever possible. So that's how you end up with that figure on the right. Is there another question? Pack is what? These are all different operations. So what you might define as one layer in the model might actually map to multiple operations, right? So pack is also one such operation, just like reshape or shape or things like that. These are all layers. So you might see conf 2D, you might see things like max pool, you might see relu, which is an activation, but often you will see other things that you don't kind of define as layers but are added by the framework itself for some internal conversion operations or some format and things like that. Things like reshape, pack, vectorize, a lot of those things are added by the framework. Okay, if there are no other questions, let's move on. So this is the other part of it, the rapids part of it. So this is the typical set of libraries that all of us have used that are kind of CPU based. So you might have used pandas, even if you've not. After reshape it will work again. TensorRT, yes, TensorRT will kind of kick in after the reshape layer here. So till that, it is, these parts are still TensorFlow units. So pandas and data frames, all of you might have used whenever you're trying to do some analytics on data that you have. For instance, you might read from a CSV, compute a number of things, statistics about the data, report it, right? And to visualize it, typically you might have used matplotlib, you might have used a bar plot, a line plot, a violin plot, various visualization APIs that matplotlib gives you. And in case you have a graph, you might have used networkx, which kind of gives you a lot more information and also some nice visualizations. Additionally, if you're trying to do basic machine learning, for instance a regression or some support vector machine or things like that, a lot of these have APIs in scikit-learn, so you might have used that too. And finally, as we've seen in this course, if you're doing deep learning, you might have used PyTorch, TensorFlow and things like this. So broadly, you have data preparation, you have model training, you have visualization, and these are various libraries on the CPU side that you use. But now what we try to do rapids. So as you know, some part of this, for instance the training itself, can be done on the GPU, right? But a lot of the visualization and the data preparation is not done on the GPU. Typically it is done on the CPU. And rapids is kind of trying to explore if you can accelerate all parts of the data science pipeline by having it run on the GPU, right? So again, is this equally beneficial for everything? It depends. It depends on the workload itself, right? As we discussed, I think a couple of weeks back, using Amdahl's law and scaling. If something is parallelizable, then you benefit by running it on the GPU. If something is inherently serial, then you might not see benefits by running it on the GPU. So, but what Rapids tries to do is at least give you the libraries and the primitives for you to be able to do this. So here the limitation might be that even though some of this can be done parallelly, can be accelerated on the GPU, you don't have the library or the ecosystem to help you do that, right? So Rapids tries to address that gap. So there are a whole bunch of alternate libraries that are listed here. This part may be common. This part, basically the difference is, if you look at earlier versions of TensorFlow, right, you might see TensorFlow CPU, TensorFlow GPU, right? So there were different versions. But now, at least with things like PyTorch, things you download one and then you just specify a device. It has become that way. But all of the other things, you will see replacements for the original libraries. For instance, here you had pandas, here you have CUDF, and where you had scikit-learn, you have CUML, and where you had NetworkX, you have CUGraph, and where you had matplotlib, you have plotly, and you have pyviz and QX filter and libraries like this, right? The CU typically stands for CUDA, which again tells you that these are GPU accelerated things. And Apache Arrow is one of those formats that helps you easily navigate these libraries. So remember that all of these deal with GPU memory, all of these libraries. So now if we look at the stack, right, this is what it looks like. So you have CUDA and CUDA libraries at the bottom, and then we typically write things in Python, and then there are things that are intermediate, for instance CUDF that we looked at here. So let's talk about the CUDF C++ library. So this again, if you notice these APIs, right, I think you had a few examples in class. It is intended to be as smooth as possible for somebody who's developing code, right? For instance, if you had certain functions in pandas and you're very used to creating these data frames and calling those functions, now if I give you a new library and tell you that it's going to run a lot faster, it's going to use the GPU, but you have to learn this whole set of APIs and you have to look through the documentation of this library, it makes it a little more painful. So if you look at these APIs, oftentimes you will see that they have the same format, the same names as the original pandas APIs. That's basically so that the transition is a lot smoother for the developers. Again, so what needs to be implemented in the library? So as an API, if I offer something like sorting or join, then I at a library level, I need to write CUDA kernels to do that, right? Because that's what is ultimately going to run on the GPU. The GPU only understands CUDA. Even if your high level language, as long as it's NVIDIA GPUs, it would be CUDA. And even if your high level code is Python, ultimately it has to be a CUDA kernel that runs on the GPU. And you need to optimize GPU implementations for all of these data types. And you need to offer primitives for this scalable ETL basically. So here is an example for a gather primitive that is implemented. And so here you find a list of operations that are supported, group wise, joins, element wise operations and things like that, and you see some support for new things also. And here is the performance part, right? So you clearly see that, so this is time in milliseconds on the y-axis, meaning lower is better. So lower time means it's faster. So you can see how much time pandas takes and how much time CUDA implementation of the same takes. So the GPU version is much faster. But again, a lot depends on how these kernels are written and how this library is implemented. And that's a very important part when you're trying to get such acceleration. So like I was saying, you follow the same APIs, right? So if you look at this, you will realize that So here, for instance, we are timing a length operation, and you see that you get some 29 seconds. So this is also something that if you're curious, you should go look up. What is CPU time? What is wall time? And again, in CPU time, what is user time, system time, and total time? Does anyone know? Just curious to see. Have you seen this before? Have you wondered what this is? Fourth line of code. I'm guessing you're going by this line number, du minus sh. So again, whenever you see Linux commands that you don't understand, the perfect page to look at them is the Linux manual page. So you can just type man space the command name, and you'll typically get a link to the manual page. So du is to estimate the file space usage. So, and the h, if I remember right, is the human readable format, right? So it reports to you in GB, and the s, I think, is to summarize. So you're asking it to estimate the file space usage for this, and it tells you that it's 1.9 GB. But going back to my original question, has someone seen the user time, system time, wall time? Any idea what's the difference between them? Okay, no one has heard of it. You should definitely go look that up, right? You learn something. So anyway, going back to our original point, here we do this with pandas, and here we do it with CUDF, and we're reading the same file, right? That's important to know from a systems perspective. And you can see that the wall time is 2 seconds as compared to 29 seconds. So that's the 10x speed up that we're talking about here. And this whole thing happens on the GPU. So you're using CUDF instead of pandas. But notice that the APIs remain the same. So you just need to change the library that you import, and everything else will work as is. And yeah, so let's continue going ahead. We're almost at 8 o'clock. Okay, fourth line again. So I've sent you the manual page to that command. Please go through it. I'll tell you what the command is and all the flags in detail. But broadly, it estimates the file space usage, right? So you're asking Linux to tell you how much file space this particular file is taking up, and you're asking it to be reported in a summarized format with human readable format, right? So that's what you get as 1.9 GB. You can try this out on your local machine also. It'll work. Just try it out on a Ubuntu or a Linux based system on a terminal, and that should work. Just change the path. You might not have this file. You can try it on whatever directory or file you have. Okay, let's see how much we have left in terms of the recap. I think we have a good bit left. So, any other questions so far? If not, we'll take a break and kind of resume in 5 minutes. But anything else that's not clear or that you want explained? Okay, if not, it's almost 8 o'clock. So we'll resume at 8:05. You can take a quick break and come back, and then we'll continue and finish the recap and move to this week's set of problems. Okay, let's continue. So we spoke about we spoke about CUDF. So again, we come back to this problem of data sets and data sizes continuing to grow. And you might want to do some sort of analysis on this, like plot a histogram or look at its distribution. And then you might want to do some feature selection, dimensionality reduction, remove some outliers, and then do some sampling, right? So all of this is part of the deep learning or the data science pipeline. So here is another technology stack where you have things like CUDF, which we already looked at. You also have things like CUML. Share all the links. I didn't share a lot of links, so I'm not sure. uh, I think you have the manual page. I can't see what else I've shared. I think there is a blog post and something on ML Commons. It would be a good idea to kind of copy links out of the meeting chat and put it onto a notepad or something like that, because in case you get disconnected, the links don't persist on meet chat. So it would be a good idea to do that as and when I post links, in case you want them. In case you don't want them, you can ignore it, but meeting links don't really persist. So feel free to copy it out as soon as I post it. Okay, so we were talking about this whole stack. So we were talking about CUML and primitives that it offers you, and then the underlying CUDA libraries, and finally CUDA itself. So here is another example where it looks similar to common Python API. So for instance, you could do clustering, which you do with libraries like scikit-learn, using some of these libraries, right? CUDF and CUML. And all of these functions, if you notice, will look very similar to their CPU library um, CPU library equivalent calls, right? For instance, this fit predict, you might see something like this, something that's very similar in scikit-learn. So you can go look at the APIs and you'll see how similar it is to the other libraries. But basically the idea is to do all those things with GPU acceleration so that you benefit from the GPU. So again, this is GPU accelerated scikit-learn. So look at the various things that it supports, right? So it supports hyperparameter tuning, which you might have heard of in the previous lectures also. But in case you don't remember, there are some model parameters itself, and there are some parameters like the learning rate that we looked at, batch size that we looked at, that are hyper parameters, that are sort of meta parameters. So before you actually run the model, you run an iteration tuning these hyper parameters, and then only proceed to do the training. And apart from that, you have support for simple things like classification, regression, and pre-processing, and a lot of clustering, dimensionality reduction, decomposition, and time series. I think you might have some internet issues. In case someone else has a problem with my voice breaking or something like that, please let me know. But if not, I would recommend you to watch the video later. Maybe you're having a bad network today, so that's okay, that happens. But I can't repeat things too much because we also need to go to the problems part of things. So you can watch the video that's there on YouTube and get back to me if you have questions. Okay, so coming to the classification regression part of it, again you have a number of varieties of regression. things like linear regression, logistic regression, and then you have things like support vector machine, k nearest neighbors. So you can see a wide variety of techniques that are supported, right? And as the library grows in terms of maturity and time, there are more things that are added to it. But basically, the idea is to support everything that a CPU version like scikit-learn supports, but give it the benefit of GPU acceleration as well. And Rapids also integrates into cloud ML frameworks like Amazon SageMaker, Azure ML, and Google AI. So you could use using this in Rapids gives you the flexibility to use hyperparameter optimization like we saw here, and a whole bunch of ML techniques. So you can get up to 25x speed ups as compared to CPU equivalents, and therefore you're able to experiment more or try out more things in a lesser amount of time. And Rapids folks also work closely with cloud providers and solution providers so that you can get access to a lot of samples and convert your code very rapidly. So we looked at these two, right? We looked at CUDF and CUML, and these I think we have already seen enough. So we'll see a little bit about these two, the visualization and the analytics side. So CU graph, again looking at the features and the user experience, you'll see performance being reported again, right? On a single 32 GB GPU, it can go up to 500 million edges. You can also scale it to multi GPUs in case you have something that a graph that goes into billions of edges. And again, a good integration among this stack, right? So horizontally as well, there is good integration between libraries because these are part of the same pipeline, right? You might want to do some analytics, you might want to do it on a graph, you might want to do it on some other data, you might want to convert between formats. So there is good integration with the other GPU accelerated libraries as well. And APIs again will be very similar to the CPU counterpart, for instance the NetworkX library that we looked at, so that they feel very familiar to you, and that's in Python. And if for people who want more control, there are C++ APIs also, and like we saw in the previous slides, there is always functionality that's going on, that's being added to these libraries. So again, this is the set of things that is supported by the GPU accelerated NetworkX, which is basically cuGraph, I think. So there's things like your in terms of components, for instance, detecting weakly connected components, strongly connected components, link analysis like page rank, and then link prediction, traversal, structure of a graph, community, things like clustering, triangle counting, and things like that. And you have support for multi GPU, you have support for query languages, you have more utilities. So this is again talking about all the things that the library supports, right? Just like the slide we had here on the GPU accelerated scikit-learn. This is for cuGraph. So I don't remember if there was a slide on the visualization part of it, but probably I don't have it here. So in case you have doubts on that, you can always ask me and I'll try to cover it in the next class. I don't see it though, so I think your slides also did not have it. So before we move to the problem solving, any other topics that were not clear? Okay, if there are no other doubts, let's move to the problem solving part. Again, this involves a lot of libraries and library names. So let's see how well you're able to. Last page, is that this? Sure, do you have any questions on this? Okay, so this is all the list of things that this GPU accelerated version of library supports, right? So you have Network X and it supports a bunch of things, just like you have scikit-learn, which supports classification, regression, a bunch of things, right? And the GPU accelerated version, basically you're talking about compatibility. How much can this new library support, or what are things that it supports versus doesn't support. So this list tells you that. So if you're looking to do graph analytics, a few things that you might commonly do are look at connected components, look at triangle counting, or look at traversal of the graph, right? Like a BFS or DFS, which many of you would have studied. So this library again offers all of these things that a CPU library offers. The only difference is that it accelerates it on the GPU. That's underneath what the library does. Its implementation helps you run the same things on the GPU. And this gives you the list of things that are supported by the library. Practically or on a different graph. No, this has nothing to do with the graph. This is just a list of features, right? I don't have examples, and I think actually showing examples is kind of beyond the scope of this live session, because we don't have that kind of hands-on examples or things like that. The only things that are shown as demos in your course itself. So I don't think there were demos shown for this part, but if you are interested and want to try out, you can go try out one of the simple examples. For instance, you can pick something like transpose or a triangle counting and try and implement it using cugraph instead of try and implement it using Network X, and then try it on cugraph. That will give you an example as to how similar the API is and how easy it is to do. So it's basically like this, right? We had a very simple example here, pandas.read CSV versus cudf.read CSV. So it will be the same thing. Some points are totally new in graph. Yeah, unless you kind of have worked with graphs, some of these things might not be very familiar. For instance, I'm sure if you're from a CS background, you would have heard of breadth first search and single source shortest path. Page rank you may not have heard of. If you have not heard of, a Wikipedia article would be a good idea to start from. So search engines, for instance, Google's search engine works on the basis of page rank, right? So the way it ranks search engine results is based on page rank. So you can go through this algorithm. But again, discussing each of these things in detail is completely out of scope of this course, right? Because in this course, what we're trying to learn is what are some of the functionalities that normal libraries offer us, and what are functionalities that the GPU accelerated versions offer us. But if you're curious and you want to understand more about these, you can go look them up. A normal Wikipedia article or even a typical Geeks for Geeks site or something like that should give you enough details. What is BFS or SSSP? Again, if you go look it up, you will find it. They are common graph traversal things, right? Breadth first search and depth first search are common graph traversal techniques. There are two different ways of traversing a graph, and again, shortest path algorithms also have different versions, like single source and all pairs, right? So you might have heard of SSSP and APSP. So you have one source and then you try to find the shortest path from that source, versus you look at all pairs of source and destination vertices. So these are again very common graph things, but like I said, it's out of scope of this course to discuss what each of these things are. So if you're interested, you can go look these up, and a basic article will tell you about it. Okay, so with that, we will move to the problem solving part. Dash is an open source library to execute end-to-end data science and analytics pipelines entirely on GPUs. NCCL, Rapids, NVML, DALI. B Rapids, okay. B. Anyone else? Okay, everyone thinks it's B. Yes, it is B. As you've noticed, the full half of today's recap was about Rapids. So again, it's an open source library which the intention of which is to execute end-to-end data science and analytics pipelines entirely on GPUs. So not just the compute part of it, like the deep learning training or inference. It could even be like an ML thing, right, where you run the classification or the regression on the GPU. The idea here is to do the entire pipeline on the GPU. Why do that? Because if you do it right, you can get some speed ups by doing that. What is DALI for? I think NVIDIA's data loader is DALI. Again, I can send you a quick link to that. That is probably not discussed in the course as such, but just knowing a one line example of what a library is would help you. It's not really just for computer vision. I think it is for images, videos and speech according to what this website says, but you can go look it up. It's a data loading library basically. Okay, let's move on. Dash is a collection of GPU accelerated machine learning libraries that will provide GPU versions of all machine learning algorithms available in scikit-learn. Any answers? CUML? CUML, okay, everybody thinks it's CUML. Yes, it is CUML. We in fact looked at that picture, right? This part where we spoke about CUML and then we looked at all the things that scikit-learn offers and all the things that CUML offers. So CUML is the right answer here. Basically, it tries to give you all machine learning algorithms that are available in the CPU counterpart. Okay. Dash is a columnar in-memory data structure that delivers efficient and fast data interchange with flexibility to support complex data models. Okay, D, Apache Arrow. Any other answers? D, Apache Arrow. Yes, it is Apache Arrow. I don't think there was a slide about this, but it was mentioned in the lectures, and it's meant to be this interchange format, right? So if you remember that whole tech stack picture, you had Apache Arrow at the bottom here. So it's an interchange format that kind of is compatible with all of these libraries. Okay. Dash is a GPU data frame manipulation library that accelerates loading, filtering and manipulation of data for model training and data preparation. CUDF, CUDF, CUDF. Okay. Yes, it is CUDF, and again remember all those examples that we looked at, right? This one for instance, and we also saw the various operations that it supports, and sorting, join, group by, reductions, lot of operations that are supported, right? Yeah, so you can use this to load by just doing a read CSV. You could do like a lot of filtering that you do, a lot of manipulation of data. So this would be useful for all of that, and it's very similar to the Pandas API. Okay, Dash is a framework and collection of graph analytics libraries that seamlessly integrate into the Rapids data science platform. A, CU graph. Okay, A, CU graph. Any other answers? Okay, it is CU graph. Again, this is something we looked at briefly. Remember this graph slide where we spoke about all of these. Network X is the CPU counterpart, and the GPU counterpart is CU graph. So So basically you need to keep these two slides in mind, right? This GPU library slide and this CPU library slide. That will help you get most of these questions right. Let's go back to that. Yes, so CU graph is the right answer. Network X is the CPU counterpart. Dash is a distributed computing project with Python interface, modular design and applicability to IT infrastructure. Dask, C, okay. Anyone else? C. Yes, the answer is C. And I think you briefly looked at Slurm in one of the very early lectures, right? So Slurm and Yarn, I think you've looked at. NPP maybe not, but Dask is the one that's kind of that's right answer to this whole Python interface and modular design. I don't think either of these offer that. Okay, let's move on. Dash is a C++ template library for CUDA based on the STL or the standard template library. Can you talk about Dask? Again, I don't think that was there in the slide, so I'll have to see if I can get some slides on that. But yeah, we can do that in the next class. B, thrust, okay. B, thrust. Don't know, okay, that's fine. This might not have been very obvious from the slides. Answer is thrust, and I've put in a link to the thrust official page. So if you look at their documentation, it says thrust is a parallel algorithm library which resembles the C++ standard template library, and its high level interface enhances programmer productivity while offering performance portability between GPUs and multi-core CPUs, interoperability with things like CUDA and OpenMP. So it basically has a very it's very similar to the C++ STL, but it's intended for GPUs. So thrust is the right answer. You might want to look at cuBLAS also later, but I don't think the others were spoken about in this set of slides, so that's okay. Okay, the next one, Dash is a rapids framework to connect web visualizations to GPU accelerated cross filtering. A, CUX filter. A, CUX filter. CUX filter. Yes, it is CUX filter. So this was the last part in the diagram, right? Where I think you had matplotlib on the CPU side, and on the GPU side you have CUX filter. This helps you to do a lot of visualization. Okay, the next one. TensorRT optimizes the largest dash possible in the TensorFlow graph. C, subgraph. D, frozen graph. Okay. C, any other answers? Okay, let's look at the answer. It is subgraph. So why is that? So remember that this is a format, right? The way in which you save the model. TensorRT looks at the portion of the graph that it can optimize, and it will try to make that as large as possible. So since that is a portion of the graph, it is a subgraph, and main graph doesn't really make sense. Frozen graph refers to the entire thing, not a portion of it. And again, TensorRT graph doesn't really capture this, so subgraph is the right answer for this one. Okay, let's move on. Dash is TensorRT's internal format used to represent the network graph before running optimizations. This may be a bit confusing. Universal framework format, okay. D, universal framework format. Anyone else? All of them sound very similar here, I guess. Unified framework, universal framework, unified file, universal file. D, universal framework format. Most people seem to think it is D. Let's take a look. It is D. Again, this is from TensorRT documentation from NVIDIA. So you can go look at it later. Stands for Universal Framework Format, which is TensorRT's internal format to represent the network graph. So so think of this as one format that TensorRT uses, right? That's all it is. And I think it was there in the very first or second slide that we looked at today. Yeah, this part. UFF stands for Universal Framework Format, which is TensorRT's internal format to represent the network graph. So you'll see a lot of frameworks having some format and some name for that. That's again a common thing. They store it in a way that is easily accessible and gives them some performance optimizations. So we have come to the end of today's session well in time. So if you have any other doubts or questions, please let me know and we can talk about it in the next class. And we're also at the 3/4 mark of the course. So overall, if you have any difficulties or trouble understanding certain things, it's also a good time to highlight it, as I said in the beginning of the class. Or if you feel things are going well and you're able to understand and follow along, then that's great, and feel free to drop off, right? I'll hang around for another 2 minutes to see if there are any questions or doubts. But thank you so much for joining and thank you for interacting, and I look forward to seeing you next week. If you have any questions, you can stay back and put them on chat. Thank you. Good source to improve feature engineering part. Yes, is kind of out of scope of the subject, but I'll see. I'll make a note of this and see if I find anything that could help you for this, and then let you know in the next class. Any other questions or comments? No problem. You're welcome. Okay, if there are no other questions, thank you so much, and I'll see you guys in the next live session.